Welcome back to another edition of The Explainer. Today, we're bringing you a clear, highly structured blueprint derived straight from industry data on how to perfectly size a commercial water heater. Listen, if you're managing a multi-tenant building, a busy restaurant, or honestly any facility that completely relies on continuous hot water, you already know how absolutely critical this is. So we're going to take all those complex engineering parameters and distill them down into a really simple, easy-to-follow step-by-step guide. Okay, let's just dive right in, all right? Because the very first thing we need to do is shatter a huge, incredibly common myth. When it comes to commercial plumbing, way too many people think sizing a water heater is just a game of guesswork. They kind of assume that as long as you buy the absolute biggest tank your budget allows, hey, you'll be fine. But actually, as the data tells us, oversizing is just as problematic as undersizing. So instead of guesswork, sizing is actually a highly precise demand-matching exercise. It all comes down to a golden rule. Your real goal is to match your facility's demand exactly. Why? Well, because if you don't, you end up with two pretty terrible outcomes. Either your system falls short, which means you're getting complaints about lukewarm water during busy periods, or your system is way too large, which leads to rapid short cycling and wasting a massive amount of money on capacity you quite frankly just don't need. To demystify all this, we're going to follow a clear 6-step roadmap today. The sizing challenge, calculating demand and temperature, the heating energy formula, factoring in recovery rates, choosing the right equipment, and finally, the final system check. All right, let's kick things off with step 1, the sizing challenge. Think of this as your ultimate blueprint. These right here are the 3 core pillars of commercial water heater sizing. We're tracking the whole journey from theoretical fixture usage, meaning, the actual sinks and showers in your building, straight through to concrete mathematical energy calculations. You estimate the demand, calculate how much the temperature needs to rise, and then convert that directly into heating energy. Moving right along to step 2, calculating demand and temperature. So to figure out exactly what your building needs, you start right here. You either measure the peak flow rate in gallons per minute or the water volume in gallons per hour. You literally just add up the expected usage across all your fixtures, every single sink, shower, commercial dishwasher, and ice machine. But here is the really crucial nuance. You absolutely must account for diversity and simultaneity. Now, that's just a fancy engineering way of saying you have to realistically calculate how many of these fixtures are actually being turned on at the exact same time during your building's absolute peak rush hour. Now, once you've got your volume dialed in, you need to calculate the temperature rise. And what's really fascinating here is how your local environment directly impacts your equipment. Temperature rise is simply your desired hot set point minus the cold inlet temperature. So take this example. If you want your water at 120 degrees Fahrenheit and your incoming city water is 55 degrees, your system has to produce a 65-degree rise. But think about this for a second. During the winter, that cold inlet water is going to be significantly colder. That seasonal drop in incoming water temperature drastically alters the actual heating load your system faces. Colder water literally means your heater has to work much, much harder. Okay, step 3, the heating energy formula. Now that we have our hot water demand and our temperature rise, it is time to apply the math. And the crucial point here is embedding this one specific magical constant into your memory, 8.33. This is a wildly popular conversion factor used across the industry. It simply represents the number of BTUs, or British thermal units, required to heat exactly 1 gallon of water by exactly 1 degree Fahrenheit. When we put it all together, we get this beautiful, simple equation. I actually like to think of this as a recipe. It's not dry, boring math. It's a super practical recipe to find the exact heating energy your system needs. You take variable 1, which is your gallons, you multiply it by our constant, 8.33. Then you multiply that by variable 2, your required Fahrenheit temperature rise. The result? That is your approximate heating load in BTUs. And if you run this calculation per hour, your result is in BTU per hour, which conveniently lines up perfectly with standard commercial heater ratings. Next up, step 4, factoring in recovery rates. Because here's the thing, calculating the raw energy just isn't enough on its own. We have to think about real-world application. Stored capacity is completely useless if the system is too slow to reheat. You've got to ask yourself, can your system deliver that peak demand and then recover fast enough for the next wave of users 10 minutes later? Say you run a busy restaurant during a packed Friday dinner service, or maybe a gym with morning rush hour showers. Your tank might handle that first wave of users no problem. But if it can't recover in time for the next wave, you are going to have some very unhappy customers. And honestly, recovery speed isn't the only real-world factor you're fighting against. I want to highlight the stakes here by pointing out these specific conditions that will silently eat away at your system's output capacity if you ignore them. We already mentioned seasonal inlet variability, but what about storage temperature and mixing losses? Or the heat you lose as water travels through long recirculation loops and distribution pipes to get to those remote fixtures? Oh, and water quality and scaling, which actively reduces your heat transfer efficiency over time. You have to calculate for these losses, or your system is going to be effectively undersized from day one. Which brings us to step 5, choosing the right equipment. Now, there is a stark night and day difference in sizing logic between technologies. You absolutely must match your newly calculated load to the specific mechanics of your chosen heater. If you're going with storage tank heaters, your sizing calculation is entirely based on stored capacity and recovery rate to meet a peak draw and recharge in time. But if you're looking at commercial tankless heaters, stored capacity means literally nothing. You must size purely for the maximum simultaneous gallons per minute at your required temperature rise. Different technologies require entirely different interpretations of your math. And it goes even deeper than that. If you're looking at boiler and indirect systems, you have to confirm heat exchanger capacity and boiler recovery. But the real game changer here, especially for facilities with highly variable demands, is using parallel staged units with smart controls. Staging multiple units smartly is for sure the absolute best way to improve reliability and completely prevent the massive inefficiencies of oversizing. Finally, step 6, the final system check. This is where the rubber meets the road. This is where we ensure all the theoretical math and the real-world factors align perfectly. Before you spend a single dime on equipment, treat this final phase as an absolutely non-negotiable checklist. Does the system actually meet the required flow and volume at your peak temperature rise? Does it recover to the set point between those peak draws? Have you explicitly included distribution and recirculation losses? And does it respect local codes and manufacturer performance curves? Walking through this checklist mechanically protects your facility from rapid short cycling and endless lukewarm water complaints. Oh, and a vital piece of advice straight from the pros. If you're dealing with complex facilities, think large hospitality operations, hotels, or multi-tenant buildings, having a licensed mechanical contractor or engineer validate your load calculations against local codes is a highly necessary fail-safe. Seriously, do not risk a massive capital investment without that final professional verification. Which leaves us with one final critical question for you to take back to your own properties. Look at your current setup, or maybe the one you're planning to build right now, and ask yourself, are your facility's peak hot water demands truly covered by a precise mathematical methodology, or are you just paying for guesswork? Take the formulas we shared today, apply them to your building, and find out for sure. Thanks so much for joining us on this edition of The Explainer. Keep learning, and we'll see you next time.